And so this invited talk, and it's going to be, I think, in a more of a tutorial sort of nature, is going to be given by Solomon. Solomon Githu is a contributor for the Edge Impulse Expert Network, and Edge Impulse has done amazing work over the last few years in democratizing and spreading the word of TinyML and Edge IoT types of capabilities. And I think the tutorials that they've released have been fantastic. And so I was really quite interested when I saw Solomon's tutorial on federated learning, where he showed how you can use things like Raspberry Pis under a federated setting. And of course, it really warmed my heart to see that the framework he used was that of Flower. And so I couldn't wait to invite him to speak to you all. So Solomon, thank you so much for joining us today. I'm happy to hand the floor over to you and see what you have for us this evening.
Hello, thank you very much. Let me first start by sharing my screen. I hope you can see my screen.
We see a PDF, looks a little bit zoomed in, and now it looks perfect.
Okay. Thank you very much, Flower, for inviting me to this talk. My name is Solomon Muhunyo Githu. Currently, I'm in Nairobi, which is the capital city of Kenya. I work as a researcher in a company that's called Wazia EP, and we major on LoRaWAN IoT applications and also AI. I'm also active in the machine learning space, and I contribute to the Edge Impulse Expert Network. And I started machine learning some few years back. I used Edge Impulse platform and some open source platforms to learn how to do it. It's a very complicated field, but with these AutoML tools, it makes things easier. And so one of the things that I realized is that there is a problem, or there is a limitation when it comes to centralized machine learning that we do. And that's where I realized that federated learning is there. And I did some digging, I did some trial with some various federated learning frameworks, and eventually I landed on Flower, and I am decided to use it because it's very easy, it's very flexible, and I also like the tutorials out there that enabled me to finish this project. So to start with, I want to talk about the classic machine learning workflow that we do. So if we want to train a machine learning model, the first thing that we do is to prepare some data sets. And this data set, it can be audio data, it can be images, or it can be maybe a CSV files with your data. We then take this data and then we train a model. For this training, we normally use high performance computers that can do this training for us. So we take the data, we put this data in this computer, and we train a model on this computer. After we train a model, we then need to validate the model. So we do a test on the model and see if the model has learned well. If the model has learned well, then we go to the deployment phase where we can deploy this model. Let's say we can deploy it in microcontrollers, like the Arduinos, the Raspberry Pis. We can also deploy our models on computers such as mobile phones and even personal computers. Uh, and this is the workflow that most people are used to. And even this is the workflow that I've been doing for a long period of time. But then there is some challenges with this centralized approach. The first problem can be data, and data can be sensitive. So if you decide to use the centralized approach, you need to collect all the data from various computers, and then you let's just send it to the cloud. If the data is sensitive, maybe it's financial data, you don't want to send financial data to the cloud. The other problem is diversity of data. Um, Normally, we tend to take data from specific sources. So you may have, let's say, one computer that is taking the data, and then you take that data, you put it to the cloud to train the model. The problem with this is that the data, it's not diverse. If the data set that this computer is collecting, if it's not diverse, then it means that the final model that you'll have, it will be biased in one way or another. So diversity is a huge problem when it comes to having just one centralized data. The other huge problem is the quantity of data. And if, let's say, for example, you have an IoT device, let's say like a Raspberry Pi, which is collecting images, and you want to train a machine learning model, let's say to identify if there's an elephant in an image. The problem with the centralized approach is that your Raspberry Pi will need to collect maybe 1,000 images. Then you decide to use a cloud computer to do the training. So you take these 1,000 images, you send it to the cloud to train your model. The problem with this is that if you don't have, let's say, good internet access, um, then there is a problem. So you can't do the actual transfer of the images files to the uh, cloud. And so that's where now the idea of having a decentralized model comes. A good example of a decentralized model is, let's say, our mobile phones. So if you have a mobile phone, you take it and you say, hey, Google, hey, Siri. Your mobile phone, it can detect these words. Your mobile phone, it also knows how you look. If I take my phone and I look at it, it can unlock the screen because it knows how Solo looks and it knows that Solomon is a person. Um, the problem here is how do we get these models? How do we get a model that can take a picture and say, this is a person and this is Solomon? Um, if you think about it, one of the things that we can do is, let's say on our mobile phones, we continuously collect audio data and let's say images. And then we take these images, let's say and then we send it to Google. So Google can do the training for the machine learning models with various data that comes from my phone, that comes from Alan's phone, that comes from John's phone. The problem with this is, again, we're taking data from our mobile phones and then we're sending it to the cloud. And our data is sensitive. And there is a lot of data that Google will need to push from our phones to the cloud. And that's where the federated learning approach comes into place, where you have, maybe you have sensitive data, or you don't have diverse data, or let's say you don't have good um, uh, bandwidth to, let's say, in IoT devices, you don't have good internet access. So basically, in federated learning, instead of taking the data, the model, we take the model to where the data is. And in this demonstration, we will use one Raspberry Pi, and we will use my personal computer. So we have two devices. Um, the first device, the Raspberry Pi, and my computer, which is the other device. They each have their own data that they are storing locally, and each device will train a model. After training the model, there is a server um, that facilitates this training. So each device will train a model. Um, After each computer trains a model, it will send the updates to the server. The server will get different updates from the different computers. It will aggregate the various parameters that it gets, and then it will come up with a final global model. And then we can take this model and maybe we can send it back to each device, or we can send it to, let's say, a cloud server, so that any device that was not in this training process can download that model and then use it. So for demonstration, we will train an image classification model that can take a picture and it can tell if there is a head or if there is a heart in an image. So our machine learning model, it will look at a picture, this picture on the left, and it will say, is this a head? Or it can look at another picture like this one on the right, where the person is wearing a safety hat, and it will say if this is a hard hat image. um, for this demonstration, the use case of the challenge here is, let's assume that we have a construction site. And in this construction site, we want to create a system which can tell if the workers are wearing their safety hats. So we can use computer vision to do some surveillance on the workers, and it can say if it only sees a head or if it sees a hard hat. If it just sees a head, and since this is a construction site, it will, let's say, create an alarm. And then the supervisor can go to the person who was just seen with their head. If we decide to use the centralized or the, let's say, traditional machine learning approach, what we will have done is, we have security cameras in construction sites, and each security camera is taking some images or some videos of the workers at the construction site. It takes those images and then it, let's say, uploads it to the cloud. In another construction site, let's say number two, you have the same thing. You have a camera which is taking um, um, videos and images of the workers, and then it's sending it to the cloud. The problem with this is we don't want to send workers images to the cloud because this is sensitive data. And again, if we decide to, let's say, collect video footage for an entire day, and then we decide to send this footage to the cloud, this footage will be so long, maybe in terms of gigabytes of space, and we will need a lot of internet data to send this image to the cloud. So the challenge here is, what if in each construction site, the security camera that's there, it can take the images of the workers and it can train a local model. So it's taking images of the workers and it trains a model to detect if there's a head or if there's a heart. In construction site number two, you have the same security camera, which is taking video footage of people and it's training another model. Eventually, these surveillance cameras, they can talk to each other in one way or another, and they can share the different models that they have trained. And these data or these updates will go to the federated learning server, and this federated learning server will then take the final updated model and will send it to Edge Impulse. So there is a project write-up for this demo project that's in Edge Impulse Expert network page. It describes all the technical details, all the choices that were made regarding the realization of this model. So for demonstration, what we will do is, we will use one Raspberry Pi and my personal computer to train a image classification model. And this image classification model, it will take an image and it can say if it sees a head and if it sees heart. And this model will be trained both on the Raspberry Pi and also on my computer. On my computer, I will also run a Flower federated learning server. And this server will facilitate the federated learning system. One of the challenges that I realized when it comes to federated learning is, how do you come up with this system? So in federated learning, you have different devices. Each device is training its own model. So how do you come up with a system whereby the devices are um, connected together? So a system whereby the server, you have like a server. The server, it can, let's say, initialize a model. It can take the initial model parameters. It sends it to each device. Each device, it will take that model. Maybe it's a mobile net V2 model. Maybe it's a YOLO V5 model. it updates that model locally. After updating that model, it goes back and tells the server, I have this new model parameters. Another device will also tell the server, I have this new model parameters. The server will then aggregate those model parameters and it will come up with a final model. So if you think about this system in a technical way, it's very complicated in terms of how can you actually do that. And this is actually why I loved Flower, because it's very flexible, it's very easy to use, and the uh, tutorials out there are really helpful. So we'll have a Flower Federated Learning Server, and this server will facilitate training image classification model both on the Raspberry Pi and on my PC. After the federated learning system, the federated learning server, it will then take the final model and it will send it to Edge Impulse. Now from Edge Impulse, we can then deploy this model to any device. So like for the training, we were training the model on the Raspberry Pi. But if we decide, let's say we want to add, let's say JSON Nano to the um, um, construction site, we can easily use Edge Impulse, because Edge Impulse, it will store final model, and we can then deploy this model to any device that can run it. So this is what we will do for this demonstration, and we will run the and then finally we will run the model locally on the Raspberry Pi using Edge Impulse. So now I want to um, go to the code that I use for this. It's not very complicated, but I will simplify it. So we need two things, or we need three things to do this federated learning. So we first need a server. I use Python to um, do this federated learning system. So I have the first Python script. So this is the server script. We also have the client script, and we have the dataset. So for the server script, here we do the importing TensorFlow, OpenCV, etc. And then we'll also use Edge Impulse Python SDK. And I will show you the use for this SDK as we go to the code. So here I have the server address, and the server address, this is basically the address of my computer, and I'm running it, and I will run the server at port 5050. The other thing that we need to do is we need an API key from Edge Impulse. So what I can do is I can um, go- so I can go to Edge Impulse, and then I can create a new project. Uh, so I can call this flower. Let me call this project flower monthly. Then now I have a new project in Edge Impulse. Note that to create a project on Edge Impulse, you first need an Edge Impulse account, which is free for all developers. So once I have my Edge Impulse account, I can go here to keys, and then I can take my API key. So it's this one. I can right click and then I click copy. Then I can come here and then I paste my API key. Afterwards, here we will define an executable, which I call modelfy.eim. I will talk about this executable later. Here we define the classes for a model. So a model will have two classes. One class is head, the other class is heart. The other thing that we need to configure is the image size. So here I'm using an image size of 160 by 160 pixels. And this image worked well for me. Note that there is a trade-off between the image size and the performance of the model. So in some cases, if you use a smaller image size, it will mean that your model it will run much faster because a smaller image means that there is less data for the computer to process. But if you have a smaller image, it means that you have less data inside your image. So in some cases, depending on the number of objects or the features in the image, um, you may need to choose between having a larger image size or a smaller image size. But in this case, 160 by 160 works very well for me. The other thing that we need to configure is the federated learning counts. So here I set 6. So what this means is that the Raspberry Pi and my computer, they will be training a model 6 times. So the first time they get initial parameters from the server, then they train a model. After training the model, they talk back to this federated learning server and they tell the server these are the new model updates. And that process will continue 6 times. Uh, the other parameter is the number of epochs. So epochs is the learning rate. So this parameter, it tells how many epochs does each client um, have. So remember, let's say for the Raspberry Pi, it's training a model, machine learning model. So it will train that model 20 times for each federated learning count. Then the other thing is the batch size. So in this case, a batch size of 8 works very well for me. And then now afterwards, we go to the main function. One thing that I liked about Flower is that it enabled me to try out various models. In this case, so here I load a mobile net V2 model, but previously I also used an efficient net B0 model. Um, when it comes to machine learning, different models have different performance. So in this case, you can see over here, like for the mobile net V2, it has a smaller footprint, so it's just 14 MBs in size. It also trains much faster, and also the entrance is also much faster. So that's why I settled with a mobile net V2. But in this use case, both mobile net V2 and efficient net V0, they both achieve the same performance. But I decided to go with mobile net V2 because it was much faster when it comes to training the model, and also the deployment part is also much faster. The other thing that do here, so we load a mobile net V2 model. Here we freeze the layers so that they don't get updated. So what we will do here is we will do transfer learning. So we have a mobile net V2 model that has been trained on a couple of objects. So what we do in transfer learning, we don't train the model again. We just update the um, model parameters on new objects or new features that we want it to learn. So that's why here we are freezing the layers of the model so they don't become trainable, but we will just update them. The other parts of code, basically, they define the layers of the model. And here we are using Keras. So here we create the model, and then here we compile the model. So here we will use the Adam optimizer. Loss will be sparse categorical cross entropy. And then for the metrics, we will be uh, using accuracy to check the performance of the model. And then here we start the federated learning server. So this is just the uh, Flower way to start the federated learning server. So one of the things that is unique in this demonstration is that we will use at least 2 minimum clients. So for this federated learning to start, we need at least 2 clients. So the Raspberry Pi will be one client and my computer will be another client. So when the 2 clients have connected, that's when the federated learning will start. And here we pass other configurations for the server. One thing that I did for this federated learning, you remember in federated learning, take the model to the data. We don't take the data to the model. So for our data set, I created individual data sets. So we have the Raspberry Pi and we have my computer. So the Raspberry Pi, it will be one client, and then my computer, it will be another client. So for each client, we have different data sets. Because in a real scenario, if you have different devices, each device will be collecting its own data. So on the data set, we have different folders for the data set. So we have one folder for the first client data set, and it has both training images and it has both um, testing images. So if we go, let's say for the training images, we have two folders. One folder is hard hat, which has the hard hat images. Then the other folder is the head, which has the head images. So we have two data sets for each client, and each client will load its individual data set in the federated learning uh, uh, server. So here we have this function which is called load dataset, and this function load dataset, it will load dataset for each client. When we look at client, the client.py script, it has an argument. It has an argument, and this argument, it will enable you to load dataset for each client. So we have So here we have the argument is called the client number. So we can pass this argument to load dataset for each client. So if let's say you have 10 clients, you can create 10 individual folders with each dataset for each client. And then you can just pass this argument with the client's number, and it will load that folder dataset for each client. After the federated learning is, so this is the load dataset. It will just load the datasets, and we have the evaluate function. So here it will, so here we load the images. So training and labeling images, that will be done by the server. And then here we have the evaluate function. So one of the things that I added here is after the federated learning has been done, the server will save the final model. And this is another cool thing with Flower is that here at the top, we are free to load any model. So if you want to load a MobileNet V2, if you want to load a YOLO V5 model, you are free. You can load it at this point. Same case here for the evaluate function. After the federated learning has been completed, the server will then save the model. So in this case, it will save the MobileNet V2 model in the saved model format. After saving the MobileNet V2 model, it will then test this model. Uh, After testing this model, we will use Edge Impulse Python SDK to profile the model and also to deploy it. And I will show this later. And that's basically it. So we have the server.py script, and this script basically it will initialize a model. After initializing a model, the clients will join to the federated learning um, server. Each client will train a model with their own data set. After the federated learning is complete, the federated learning server, it will save the model first, and then it will use Edge Impulse Python SDK to profile this model and then to deploy this model. I will talk about this profiling and deploying later. So what we can do to start this federated learning is we can run Python server, we can run the server.py script. So I will start the server script over here. And then here I have my, on my computer, I will start the client script. And remember, we have an argument, client number, that we can use to load data set for individual client. So in this case, I want my computer to be the first client. So I will pass the in client number argument, I will pass number 1 to specify that this is the first client and it will load the first folder. At the same time, here I have SSH to a Raspberry Pi. And here on the Raspberry Pi, I have so this is the Raspberry Pi. I have the client script and I also have the dataset folder. So this is the uh, folders on the Raspberry Pi. So we have the client script and we have the dataset folder. So I will tell the Raspberry Pi to run the client script, and for the client number, I will pass the number 2 to specify that this is the second client. And if you go to the server logs, we can see that the server, it has loaded the training images. It has initialized the model, and now it's waiting for the federated. And now this federated learning has been started. If both clients have connected, so my PC has already connected, and it's now training a mobile NP2 model. And if you go back to the Raspberry Pi is also training the model. Because of time, I will just skip this process because it will take quite some time for this uh, to finish. But I have some logs that we can look at um, regarding the processes. So here we have the server logs. So the server so this is the server. The server, it will initialize the initial uh, global parameters, and then it will evaluate the initial parameters for each federated learning count. So this is the first count. The server will um, aggregate the various model parameters that it has received from each client. And this will continue for 6 times that we defined in the client in the server.py script. If we look at these server logs, we can see that the model has an accuracy of 0.5. So this is initially, and then the accuracy goes up to 1. One reason that could be the cause of this is in this case we are using a mobile NP2 model, and we are just doing a transfer learning. In this transfer learning, we want the mobile NP2 model to detect if there is a head or if there is a heart. Now these two images that we are showing the model, they are not very complicated model, they are not very complicated objects. So the mobile NP2 model, it may be learning easy for this particular task. That's why we can see that the accuracy, it's always 1, because it's not a very difficult task that we may be giving the mobile NP2 model. Finally, after the federated learning, the server will then save the model. So here we can see that the server has saved the model. And here on the folders, we can see that there is a saved models folder, which has a mobile NetB2 model over here. So this is one thing that the server does. So this is the final model that the server aggregated from both the Raspberry Pi and also the PC. And the server will also test the uh, final model. So in this case, for the testing, we can see that the server, it tested the the final model on an hard image. And the model actually predicted fine. It looked at one image and it correctly predicted that that was a hard image. And here we can see that the performance of the model is actually fine. Afterwards, afterwards, the server then uses the Edge Impulse Python SDK. And here we can see this function for the profiling and deployment. So one thing when it comes to machine learning models, we want to know performance of the model. So in this case of IoT devices, not every model can run on any device. You can't take a YOLO V5 model, then maybe you run it on an Arduino. So one of the things that we can do with Edge Impulse is that we can actually profile this model. And by profiling means that we will get the performance of the model. So in this case, we profile the model for the Raspberry Pi 4. And we can see that the here we can see the performance of the model. Like the time per inference of this model is just 54 milliseconds, which is actually quite impressive. You can also see the RAM and also the um, ROM or the flash consumption of this model uh, using the profiling. And so the profiling, it enables you to get an overview of your model, which MCUs and also which computers can your model run on, and also the performance metrics of your model on these various devices. So here we can see the logs for profiling the final model for the Raspberry Pi. So the time by inference is 54 milliseconds. And here we can also see a performance on other devices. So like for the Cortex M0 devices running at 40 uh, megahertz, we can see that this model is actually supported for these devices. And the time per inference here is actually quite high because it's at 370 milliseconds. But again, we can optimize this model by maybe selecting uh, mobile, another model. So in, instead of maybe selecting MobileNet V2, we can select another model. Another thing that we can also do is, if you remember, we used an image size of 160 by 160. We can, let's say, reduce this image to, let's say, 48 pixels by 48 pixels or 96 pixels by 96 pixels so that our model can become less resource. Um, uh, it can consume less resources on the devices. So here we have logs for profiling on various devices. So here our model is supported on high-end MCUs. It's supported on accelerator boards like the Renesas boards, uh, the Renesas board, the NVIDIA board. So here we can see that it's supported there. It's also supported on MPUs like the Cortex A72. It also supported on GPU or MPU accelerators. Um, and we can see here, like for the GPU or MPU accelerators, the time per inference is just 9 milliseconds. And but if we see for the low end MCUs, we can see that the time per inference is 370 milliseconds. And we can relate to this performance because a high-end MCU means it has more resources to run our model, but a low-end MCU, it will struggle a bit. So that's why the inference time is actually quite high. Now, once the profiling is done, if we go back to Edge Impulse, uh, so if we go to Edge Impulse, we'll actually see our model. And one of the things that Edge Impulse recently added is bring your own model. So you can actually bring your own model to Edge Impulse. And this is actually one of the things that this project does. So the server, it will aggregate the final model. And then this final model, it will be sent to Edge Impulse. And here in Edge Impulse, if we go to upload your model, we can see that the model has been uploaded to a Impulse. So what we can do here is we can do some configurations. Like here, the model input. This is an image classification model, and it takes RGB images. The for the image processing, the pixels are not normalized, so we can select this. And the model output. This is an image classification model, so the output is a classification um, class, and the labels are head and hearted. The same things that we defined in the server script are the same ones that we select over here. And our model is now on Edge Impulse. So one of the things that we can do is if we come here and we give our model, let's say this image, we can test this model on an image. So here I've given this model this image. So this is an image of a person with a safety hat. And in our problem, this is a hard hat image. And we can see that our model has correctly predicted that this is a hard hat image. From there, we can further test our model. So on Edge Impulse, I have a couple of images that I have uploaded that we will use for testing. So I can come here to data acquisition, test, and here we have a couple of images. So this is an image of a person with a hard hat, and the label or the class of this image is hard hat. So we can see another image of a person with just a head, and the label for this image is just head. So we can go to model testing, and then we can test all the images with this model at once by just clicking this button over here, and the model will be tested on these images. So initially, the model um, it achieved an accuracy of 93%, which is impressive. And from here, we can then go to the deployment. So one cool feature with Edge Impulse is that you can deploy your model to a wide range of devices. So we can, let's say, create libraries from our model. So Arduino libraries, C++ libraries, STM32 libraries, etc. We can also target various devices like the Arduino 33 BLE, Arduino Nicla, um, which other devices, Renesas, its studio boards, Sony boards, and such. In this case, I want to run the model on the Raspberry Pi. So on the Raspberry Pi, I have installed Edge Impulse for Linux, and I'm with Jet Impulse for Linux. If we want to uh, download a model from Edge Impulse, so what I can run is So what I can run is so I can run this command to download our model. So this command, it will download our model from Edge Impulse as an EIM executable. And to explain what the EIM executable is on here on the Raspberry Pi, of SSH on the Raspberry Pi, I will run this command Edge Impulse Linux runner, and then I will give it the model file. So if we look at this directory, we can see that there is this EIM executable over here. And I will run this EIM executable on this terminal. And right now the model is running on the Raspberry Pi. If I go to the Raspberry Pi here, so if I come here, I can see a feed of the Raspberry Pi. So here I can show the Raspberry Pi, let's say an image of a person. So here we can see that the Raspberry Pi is classifying that this image is actually a person's head. So I can show the Raspberry Pi another image. So like this one over here. And we can see that the Raspberry Pi is correctly classifying these images. I had a project over here, but Windows decided to do some update, so I will use my phone to project. And basically, what the Edge Impulse Linux runner does is I have a Raspberry Pi over here with a camera, and so what's happening is that we are getting an image from the Raspberry Pi. We take that image, we process that image, and then we give this image to the model. And then finally, the model, it will also give us the uh, output. So here we can see it's taking 38 milliseconds to classify this model, and you can see the predictions over here. And all of this is running just by running this command over here. So the executable here, it's called an EIM executable. And this executable, it has your signal processing and also your machine learning model in just one executable. And then using the Edge Impulse Linux, it enables us to get images from the Raspberry Pi camera, and then we pass these images to the machine learning executable, which will do the processing and also the classification. Um, and then we will get this live stream from the Raspberry Pi over here. And so that is basically it when it comes to federated learning. So instead of taking all images and then putting it to one computer and then training the model over there, we can train the model on various computers. And then let's say we take the final model, we push it to uh, cloud server like Edge Impulse, and then we can deploy this model to any device, provided it can uh, run the model. And yeah, that's it from me.
That was really cool.
Questions?
Yeah, thank you so much. I really appreciate the depth that you went to there. I think people are going to love this tutorial, um, and I'm sure like a lot of people are going to end up watching and following up. Unfortunately, we're running a little bit low on time, so I can't really take questions right now. But I think what we can do is look for opportunities maybe through our Slack to collect a few questions and pass them along to you. If you, I'll follow up with you and think we can do it that way because this is really great content I haven't seen anywhere else before, and so we're always, super excited to bring that type of content to our folks. Thank you so much, Solomon. That was amazing. That was great.